So welcome back to the first of our 3 talks this afternoon. And we have up Mike Miller, one of the organizers of the conference, who is presenting joint work with James. Why Go Effective?
Thanks, Doreen. Okay, so, and I should say, Doreen and I don't know, well, I won't speak for Doreen, but Doreen and I are helping Chris with this conference, but the lion's share of the work fell to him, and thank you, Chris, for everything that you did to make this happen.
This is true.
It's always it's a great event, and we're really happy to be able to help in whatever way we can. Okay, so what I'm going to do here is present work that James and I have been talking about for quite a number of years, but which I think, at least in my case, have only started to feel somewhat confident that I've got a compelling story to tell relatively recently. And so, and through that process of talking with James, it's also become clear that while we agree on a whole bunch of stuff, and I think most of the important stuff, there's also important respects at the end of the day in which, on at least some of the issues that I'm going to be discussing here, we ultimately might want to go in slightly different directions. And partly for that reason, and partly for the reason that I might just make obvious mistakes, I'm going to be speaking in the first person singular so that James is off the hook for whatever kind of blunders are ahead. So, so as I think the discussion yesterday already started to kind of presage, and some of the issues under discussion this morning started to highlight, quantum field theories can be understood as effective field theories where, for now, by that I'm just going to mean something relatively loose, namely that they're theories where we think that there's an explicit restriction on their domain of applicability. So there's parts of the world which we don't hold the theory ontologically responsible for. We only want to hold it ontologically responsible for some part of the world. And I think, okay, this kind of picture was, of course, developed in the context of quantum field theories. It eventually gets employed beyond the scope of quantum field theories in particular, and to different kinds of physical theories. And I think part of the reason that we only arrived at this methodology in the context of quantum field theory in particular is that an important class of quantum field theories, the empirically adequate ones as far as we can tell, need to be understood as effective theories in order to be well defined. Okay? And I'll say a bit more about the details of what I mean by that as we go, but I think for now I just want to offer that as a kind of suggestion about why we've only stumbled upon this methodology at this particular stage in the scientific project, whereas I think once you see the methodology in front of you, what you've actually got on offer is the kind of methodology that is sort of puzzling why we weren't doing it all along. Okay. And I think, so as a bit more scene setting, a number of authors have recently advocated for a new form of scientific realism, namely effective realism, which is aimed at leveraging the kind of technology that one gets from the effective field theory framework into articulating a kind of scientific realism which allows one to evade certain kinds of arguments that get leveraged against the scientific realists that express their realism in alternative ways. And the core idea of that program is to restrict our ontological commitments to the regimes where we have empirical access, or where we don't feel that we're too far away from having empirical access to make well-warranted claims about what the structure of the world looks like. Okay. Now, I count myself in this camp. I believe that some version of this kind of effective realist picture is the right way to think about quantum field theory. I think it's the right way to think about physical theories more generally than that. But what I'm going to be concerned with here is that I think, at least in some discussions, not exclusively amongst philosophical attention to these theories, but amongst physical discussions of these theories as well, the motivation for adopting the view of effective theory, effective field theory, has been kind of incorrectly bound up with the need for renormalization in quantum field theory. Those two ideas are deeply intertwined with one another, and as we saw this morning, what we even take the renormalization problem to be, what we take renormalization methodology to be, is something which changes drastically over the development of the course of quantum field theory. And I think parts of that kind of development, those developments have left kind of relics inside of the way we talk about at least certain kinds of motivations for effective field theory that don't belong there in the motivation for adopting that picture of the framework. And what I'm going to try to do here is three things. So first, I'm going to try to disentangle the motivations for effective realism from the renormalization problem. And on this point, I'm going to state my case probably more strongly than is warranted by the arguments that I have to offer here. That's for a reason. I want to kind of establish, at least as a datum in the debates about this, that there's at least one way of thinking about these as conceptually distinct in a pretty strong sense. The sense I'm going to advocate for here is probably too strong, and I hope that when you all push back on me, we might see a way to a more stable, well-defensible position. And then what I'm going to do is articulate what seem to me to be the right motivations for adopting effective realism, which come from considerations that just aren't internal to quantum field theory at all. They're rather concerned with the nature of the empirical access that we have to the world in front of us and the kinds of reasonable expectations we can have about the epistemic access that we have to the world. Okay, and finally I'm going to respond, there's been at least one critical kind of commentary about this kind of effective field theory picture, effective realism picture, due to Laura Ritchie. This is, I should say, the first of her criticisms. She's, I know now, working on a bigger tranche of criticisms, but what I'm going to respond to here is her worry in this 2018 paper. Okay, so to get there, I'm going to first kind of recite to you a catechism that I learned to recite when I was first studying quantum field theory, and that involves lots of pieces that I think are exactly right, but it mixes in ingredients that, at least in certain ways of saying them, strike me as mixing together things that don't belong together. Then I'll get to telling you what I think is wrong about what gets mixed together, which is namely the actual reason why perturbative ultraviolet divergences are there in the theory, and then I'll turn to this question of why adopt effective realism. Okay. So, in the framework of quantum field theory, as you all know, to express a particular theory, we begin by specifying some Lagrangian. That's going to determine the number of and kinds of fields present in the theory and the nature of the physical interactions obtaining between those fields, if there are any. And if you write down a physically interesting Lagrangian, in the sense that it's a Lagrangian that captures the kinds of interactions that we think actually obtain between the kinds of microphysical objects that quantum field theory describes in the real world, we can't solve the resulting theory exactly. We need to resort to a tool perturbation theory for attempting to extract information from this perturbative expansion in the hope of getting information about what a realistic interacting theory might look like. There's other tools for getting at what realistic interacting theories look like, which use alternative tools, such as regularizing theories on the lattice. Those methods are not perturbative in the sense that we need not use perturbation theory when we use the theory in that way. We can evaluate observables numerically, say. But in that case, again, what we're doing is we're departing from what, by the lights of the formalism of the theory, would be an exact model of the theory in kind of the philosopher's sense. Okay. So what the perturbative evaluation of the observables reveals is that the individual orders of perturbation theory are infinite, and they're infinite, at least in one instance, because of the ultraviolet or very short distance or very high momentum end of an integration that one needs to do in order to calculate the value of that term. There's a different class of infinities at the other end of the integral. So I'm reciting the catechism. Parts of what's here I don't believe at all. But okay, this is what I was told. There's a different class of infinities at the other end of the integral, conceptually unimportant. Don't really believe that. And for reasons that are going to become clear in a moment, we need not consider the question of whether the perturbative expansion converges. We're going to have our hands full just getting to grips with what's going on with the first few orders of perturbation theory. So the infinities from the large momentum or short distance end of the integration necessitate the renormalization of the theory. And in the early days of quantum field theory, this was handled in an ad hoc manner. Infinite counterterms were being added to the Lagrangian in order to cancel infinities, and this was just theorists sweeping infinities under their office rugs. But eventually, what we learned to do, why we needed to do this step, there was a physical reason underlying the need for this process, and namely, our first guess at the Lagrangian was expressed in terms of unmeasurable Baire quantities. The unmeasurable feature of these quantities, you might think on certain strands of operationalism that are, I think, lurking in the background in at least some of these discussions. Those unmeasurable quantities are unphysical, and hence the theory isn't really responsible for even making sense of them. Adding counterterms to the Lagrangian allows us to re-express the theory in terms of the physical quantities that are actually observable and hence physically meaningful. Now, what was learned is that that process can go better in some theories than it does in others. And in some theories where it goes well, only a finite set of redefinitions to parameters in the Lagrangian are required to cancel all of the infinities arising at every order of perturbation theory, and those are what are called the perturbatively renormalizable theories. Those redefinitions require that we input measured values for some physical quantities into the theory, but that's fine. That's something we do all over the place in physics, and there's nothing particularly mysterious about that. Other theories, on the other hand, are less well behaved, and they require an infinite number of redefinitions to cancel their infinities to all orders of perturbation theory, and those theories are called the perturbatively non-renormalizable theories. And those theories were initially regarded with great suspicion. After all, they require an infinite number of measured values as input in order to cancel all of the divergences in their perturbative expansion, and so in order to characterize them exactly, we need to somehow feed the theory an infinite amount of empirical information, and it's hard to understand in what sense a theory like that is really genuinely predictive, or could be made to be genuinely predictive. But with the development of the renormalization group that was discussed this morning and the effective field theory framework, we realized that these non-renormalizable theories aren't so bad. We can put in a short distance cutoff or a high energy cutoff in our effective treatment of the theory, and in this way we remove the dependence on the large momentum scales in the theory by freezing them out. And the renormalization group tells us how to execute the redefinitions, or it at least helps direct us in determining how to execute the redefinitions of the parameters in the Lagrangian. And in so doing, it also shows us how those couplings scale with energy. And now we can even measure that scaling, and it matches what, at least in the QCD and QED cases, it matches what's there in the theory. So if we're willing to accept a bound on the precision of our theory, even non-renormalizable theories can be rendered predictive and consistent with only a finite amount of empirically determined input. And on this kind of way of proceeding, one even gets an explanation of the original difficulties with infinities. The theory was crying out, telling us that it was going to break down at some large momentum scale. And by cutting it off, what we did was we recused the theory from telling us about the regime where it gets into trouble. So what was realized kind of next in the kind of conceptual progression is that not all renormalization group flows are created equal. Some theories yield a flow that shows the theory possesses a well-defined continuum limit, in the sense that it's going to be possible to remove that cutoff that we put in to regulate the infinities, and remove that cutoff and get a well-defined, consistent theory on the continuum. And that turns out to be the case in theories which are asymptotically free, where in the limit in which the cutoff is removed, the couplings come to zero, and that seems to be the behavior of quantum chromodynamics. It's also the case in theories which are asymptotically safe, which is a related but slightly different property, where in the limit in which the cutoff gets removed, the couplings all go to finite but non-zero values. There's been debates, and I'm not going to have anything helpful to say about these debates. There's been debates about whether or not general relativity treated as quantum field theory might exhibit that behavior, but there's no conclusive evidence either way at this stage. We do have examples of at least toy models that exhibit this behavior, though. But not all theories exhibit renormalization group flows that show them to possess a well-defined continuum limit. Sometimes in the limit where the cutoff is removed, the values of the coupling diverge for finite values of the cutoff. This is the Landau pole behavior that Alex was pointing us to this morning, and multiple lines of evidence suggest that this is the fate of quantum electrodynamics. And so quantum electrodynamics, if that's right, doesn't have a well-defined continuum limit. There's other ways to exhibit similar kind of closely related phenomena. We think that the elementary scalar Higgs field in the Standard model exhibits this phenomenon of triviality, where the only way for the flow to arrive at a Higgs point is to turn off the interaction altogether. And for this reason, the currently available evidence, I think it's fair to say, suggests that the Standard model, just like quantum electrodynamics, is going to fail to possess a well-defined continuum limit. So all's not lost, however. We can leave our cutoff in the theory and treat theories with the bad non-perturbative ultraviolet behavior effectively, only hold them ontologically responsible for I stated this differently on the slide. So we don't need to hold them, those theories ontologically responsible for the very short distances and very high energies at which those kinds of ultraviolet defects of the theory become manifest. We can allow them to be predictive and give us good information about the relatively long distance physics that the Standard model describes, where by relatively long, I mean relatively long with respect to, say, something like the Planck scale. So that's to say, we can ask them to give us something less than a correct description of what there is across all distance scales. And when you when you set the parameters of the game up in such a way that you say what it would be to be an exact model of the theory that I'm writing down is for there to exist this well-defined continuum limit, what you're asking is for the theory to give you a description of what there is across all distance scales, from the very longest to the very shortest. Instead, we can ask what there is on the limited range of scales where the theory yields a coherent physical picture, and that seems to be the way to understand theories like QED and the standard model. Now, we must understand non-asymptotically free and non-asymptotically safe theories in this way, as far as I can tell. And it's, I think, worth noting that nothing stops us from understanding the asymptotically free and asymptotically safe theories in that way as well. Just because a theory enjoys a continuum limit, that doesn't mean that I'm not allowed to use this new effective methodology that I've developed in order to cut off at some scale beyond which I no longer feel confident that I've got sufficient empirical information to believe strongly that the structural characterization of that regime matches on to what's there in the theory. Just because I've got a continuum theory doesn't mean I've got to read it as such. Okay, so that's the kind of background story. I think there's loads of pieces of the story that are exactly right. And what I want to do here is just point to at least one place where I think there's something slightly misleading, or at least where we're mixing together two kinds of things that don't seem to me to belong together. Okay, so the problem with the catechism, as I've just recited it, is that it suggests that the origin of the perturbative ultraviolet divergences is physical in nature, in some sense. And it suggests that the need for perturbative renormalization is bound up with the motivation for treating quantum field theories as a vector theory. On the contrary, I think perturbative ultraviolet divergences are a purely mathematical artifact, and the motivation for adopting an effective understanding of quantum field theory, here's where I'm putting things rather stronger than I think I've probably got an argument for, but I'll put it the strong way here. The motivation for adopting an effective understanding of quantum field theory has nothing to do with their presence in a given theory. Okay. That's the strong version of the claim. So recall the part of the catechism where we tell ourselves that the presence of infinities in the theory is the theory crying out to us, telling us that it's going to break down at some large momentum scale. Okay. I think that that claim is misleading. And I think it's misleading because, okay, let's try to consider the ways you might construe that claim. So you might understand it as saying that the presence of perturbative ultraviolet divergences signals an eventual breakdown of the theory at some large momentum scale. But if that's what we mean, then it's hard to see how the claim applies in the case of the renormalizable asymptotically free theories like quantum chromodynamics. There we think we have good reason to think that there's going to be a well-defined continuum limit for the theory, even though it has these perturbative ultraviolet divergences. And so if that's right, then there doesn't seem to me to be a breakdown for the divergences to be there signaling. And other theories with perturbative ultraviolet divergences have Landau poles and fail to have a well-defined continuum limit, such as quantum electrodynamics and the Standard Model. But in those cases, it's just not totally clear to me what the connection between the perturbative divergences and the eventual blow-up of the physical couplings at finite cutoff is supposed to be. This is part of the story that, or this is mixed into the story that Alex was telling us this morning. But at least to me, if we take those to be the infinities at issue, then the infinities are constitutive of the breakdown of the theory, not a signal that it's happening elsewhere. So if that's okay, then what the catechism gets wrong is that it treats perturbative ultraviolet divergences in a sense as like part of the physical content of the theory, in some perhaps a sense of physical that requires further explication. And I think what makes that wrong is that the perturbative divergences are demonstrably mathematical artifacts that don't have physical content. Here's what I mean. This is the kind of diagnosis of the perturbative ultraviolet divergences that emerges from this causal perturbation theory literature. So to see that these things are artifacts of perturbation theory, we just need to look at the standard expression for the two-point function. So look at the left-hand side. inside of the expectation value, you've got what masquerades as a time-ordered product of two functions of the space-time coordinates, but something that we've learned is that those quantum field operators aren't operator-valued functions anywhere in space-time. Those things that look like functions are actually distributions. And some of the, so what appears to be multiplication of functions inside of that two-point function is actually multiplication of distributions. And while functions nicely pointwise multiply with one another, same is not always true of distributions. Whether or not the multiplication of distributions is well defined is very sensitive to the singular support of the distributions and whether or not they have overlapping singular support. So integrating products of distributions with the wrong kind of overlap in singular support can yield divergences. And now note that if you regularize the theory with some cutoff, you also remove the overlapping singular support from the domain of integration. And since the cutoff is usually given some kind of physical interpretation in standard approaches to renormalization, it isn't hard to see how those perturbative divergences, which I'm claiming are mathematical artifacts in some sense, get dragged into the physical picture of the situation. They're just the place where you're cutting off. By cutting off, you're cutting off this the place where the bad multiplication is occurring. So the causal perturbation theory program that James was mentioning demonstrates that we can write down a perturbation theory order by order without ever encountering perturbative divergence. But when we do that, we still need empirical information to fix ambiguities in the distributional products, okay? In order to render those products unambiguously defined, we need to input information. We need to give the products typically some fixed coefficients. And in renormalizable theories, a finite amount of information suffices. In non-renormalizable theories, we still need an infinite amount of information. And so in the causal perturbation theory way of constructing the perturbation series, the way that proponents of that kind of picture think about things, the kind of information that you're feeding in to disambiguate the distributional products is directly analogous to the coefficients of the counter terms that you originally wrote down in the standard renormalization prescription. So does any of that have any bearing on the question of the existence of the non-perturbative continuum limit of the theory? So if you're worried about the perturbative ultraviolet divergences and you cut off in an effort to remedy them, there's a sense in which you're also kind of bracketing questions about the non-perturbative ultraviolet completion of the theory as well. And once we remove the perturbative divergences using standard renormalization, or if you choose to do so, recast the theory using causal perturbation theory so that they never arise, then you can kind of face up to this question of the non-perturbative structure of the theory. And what I think that process shows is that perturbative divergences don't really bear on the issue of whether the theory has an ultraviolet completion. The question of whether there is an ultraviolet completion of a given interaction or a given theory is a physical question about the nature of the interaction that we originally input into the Lagrangian, and then what the scaling behavior of a theory with that kind of interaction inside of it looks like. So those theories without an ultraviolet completion need to be treated as effective in order to be well defined. And as I said, I think that includes the standard model of particle physics. But whether or not that's the case, I can't see a direct connection, or at least not one that's sufficiently clear to me, to whether or not there are perturbative divergences in the theory. Okay, so what we've seen is that so far, some quantum field theories need to be understood as effective field theories in order to be well defined. And I think what strikes me as a fact, though, to be fair, like that's really a reflection of our best body of evidence about these theories. There's loopholes and so on, but I think it's the best. Our best evidence suggests this, and I think that is partly what gives people some kind of disquiet. It's like what we were after was this project of writing down the complete microphysics of the world. That was at least as some people conceived it, that was the original project of quantum field theory. And now you come along and say, well, you can't have that. What you get is something less exhaustive than that, less complete than that. And so when you tell at least some people that some quantum field theories, including our best effort at the microphysics of the world, have to be understood as effective, and in order for them to work, they can't be exhaustive in that way. They can't tell you everything that there is to say about the microphysics of the world. That makes people feel uncomfortable, and I think it's a little bit like a shotgun wedding kind of reaction. It's like, if you want to have this thing that everybody clearly playing this kind of game wants to have, you've got to somehow adjust your expectations about what the physical theory can deliver to you. Okay, and so what I want to try to do is, so I think that this is just true. It's true that we need to construe these theories as effective theories. But I want to try my best to articulate grounds for adopting this effective field theory methodology that just don't that don't come from this kind of forced pressure that we happen to have in the case of these particular models. So what's true, I think, is that the fact that some quantum field theories require an effective treatment to be coherent or well-defined, or however you want to characterize it, explains why effective field theory methodology was originally developed in this context. We were forced to do so. But once you have that methodology in hand, we should be taking theories to be effective theories, independently of whether they need to be treated as effective in order to be well-defined. And I think, in fact, independently of whether they're quantum field theories at all. The motivation for going effective comes apart from the renormalization problem, understood as the problem of canceling perturbative divergences, and I think it even comes apart from the issue of the existence of continuum limits of quantum field theories. So what are the well-founded reasons for, or what strike me as the well-founded reasons for going effective? Well, I think that demanding that our theory has a well-defined continuum limit is to demand, well, it is to demand that our theory is valid down to arbitrarily short distances. And I think that demand forces us to be ontologically committal about regimes where we just have no empirical access and likely never will. And that's the kind of thing that makes me nervous, and that's the kind of thing, if you followed scientific realism debates, which puts you in a position to overcommit ontologically and kind of make yourself susceptible to be undermined by future developments in physics. Treating theories effectively, on the other hand, can bring our ontological commitment in line with the kind of empirical access that we actually have to the domain that the theory describes. And by inserting the cutoff, we give ourselves the resources to adopt the epistemic attitude that we don't trust what the theory has to say about the world in the regime with beyond the cutoff. Now, in some cases, we have positive reason to expect that the theory is going to become untrustworthy below that cutoff. The standard model is going to be untrustworthy at the Planck scale, we expect, for example. But even in cases where we have no such positive reason to expect that the theory is going to break down, we can still express the epistemic attitude that we only want to be ontologically committed in regimes where we have empirical grounds for thinking that we understand the physics. So some advocates of effective realism stop with this epistemic kind of thesis, and I think maybe James feels more comfortable with that kind of epistemic reading of things. I, on the other hand, think that there's this kind of methodology opens the way to doing something a bit more radical in terms of adjusting the semantics of our theories in a way that's faithful to the relevant kinds of epistemic constraints. And so on that approach, I think we can regard the claims that an effective field theory makes about physics above the cutoff, physics in the regime where we've got good empirical control over the situation as, in fact, true. And this kind of semantic reform mechanism, which, to be fair, requires much more detailed elaboration than I'm going to be able to give you here, gives us a way to understand what we've been doing when we've been using non-fundamental theories as a basis for ontology all along. Okay. And moreover, I think it also opens the path to a kind of unified account of the semantics of theories across all physical theories, whether they're contenders for non-fundamentality or non-fundamental theories. Okay? And that kind of unification of the way we handle how physical content gets into the mathematics of our theories is something that I, in particular, find very attractive in a view of the semantics of theories. I don't see any particular reason why the semantics of theories ought to work one way for the non-fundamental stuff, and then magically, once we get down to the purportedly fundamental, that some new semantics is going to kick in. Okay. So here again, I'm going to state a position that's probably stronger than I've got well-founded arguments for, but I think it's worth having in the water. So even if you found out that quantum gravity treated as an effective field theory was asymptotically safe in the standard model, contrary to currently existing evidence, had a well-defined non-perturbative continuum limit without a Landau-Paul, I'd still want to read that whole thing. So that is to say, if all of contemporary physics, modulo issues with dark matter and dark energy, and probably other important things that I'm missing, but all microphysical goings on could be wrapped in a complete quantum field theoretic description with a well-defined continuum limit, I'd still want to read that whole thing as effective field theory. And even if there are no empirical anomalies, even if over and over the theory just got the right answers about what we were calculating, there's still a kind of skeptical worry one can have that there are more scales far below the relevant one in the hypothetical quantum gravity theory, which could have new physics. And one of the morals, one of the kinds of features that effective field theory approaches have made manifest is that it's not hard to arrive at situations where you can have complicated, relatively short distance physics to which the relatively long distance physics is just immune. It doesn't make any difference for the long distance physics what happens to be going on the shorter scales. And so, and this is the phenomenon of what's called decoupling. There's lots of technical conditions which determine under what circumstances this is like an exact kind of separation, and we don't have those sorts of things in the scenario that I'm imagining exactly. But I think in working with effective field theories, what we've learned is that it wouldn't be at all surprising that there were physics at shorter distances, which just isn't going to show up in the relatively long distance physics of the standard model set. Okay, so if that's true, that's an okay way of thinking about things, then it's kind of hard to see how we could ever feel like we have compelling evidence to think that there's nothing lying below the kind of stable level of reality that our effective theory is capturing. We can't observe those scales. It's plausible that there's going to be scales which we can never give ourselves empirical access to. And if the phenomenon of decoupling is obtaining in the relevant cases, we're not going to be able to indirectly confirm claims about what's going on down below either. So I think, oh, sorry, okay. I seem to have dropped a slide here. But so what I think is that what this means is that the claims of something like the standard model could just turn out to be true in the same kind of attenuated sense that claims of other non-fundamental theories are, like, even if we don't happen to uncover what sort of microphysical structures there are lying below. So standard accounts of the semantics of theories don't make space for that kind of move, at least not as far as I can see. And I expect that it's at that stage of semantic reform where many are going to find defective realism defective, or at least not yet fully articulated, and I think that charge at least is very fair. But the most incisive criticism of the view that I'm advocating, at least that I know of, is to be found in this paper from Laura Ritchie in 2018. And her worry is that the use of the renormalization group requires that we make quite restrictive assumptions about the space of possible theories. So the kinds of influences that the renormalization group shows the long-distance physics to be insensitive to are just the kinds of influences from below that there would be if what's down there are quantum field theoretic degrees of freedom. That's the kind of insensitivity that the renormalization group analysis is able to give you. But her argument continues, there's much more exotic things that could be lurking down below, and the renormalization group doesn't tell us anything at all about how those things might show up in our physics, at least not explicitly. So it seems like in adopting effective realism about, say, the standard model, we leave ourselves wide open, according to Ritchie's kind of view, to getting the hidden gears and springs of reality dead wrong. So the shortest distance physics could fundamentally be about strings in 26 dimensions, or something else as yet undreamt of, and here we are claiming that there really are quantum fields in our scattering experiments at 10 TeV. So, conclusion of her argument, doesn't effective realism just collapse into some kind of empiricism? Aren't we just saving the phenomena at some relatively long distance scale, and aren't we likely to just shown to be wrong about what the hidden gears and springs are? And I guess my answer is just, I don't think so. I think it's entirely possible, in fact, probably likely, that what lies below the cutoff that in the standard model treated as an effective field theory is going to show that the quantum field picture does get the hidden gears and springs importantly wrong. We certainly don't have any way to rule that out. Nothing about effective realism, as I understand it, rules out such a possibility. And I think I'd be doubtful of any realist view which purports to do so, given the nature of the empirical access that we've got in this particular situation. The claim of the effective realist that extends beyond mere empiricism, though, at least as I understand it, is that whatever lies below the cutoff is going to reproduce a world like the one described by the effective field theory on the scales where we trust the effective theory. So when we say that property descriptions of medium-sized dry goods are true, we get wrong what objects there are and what properties they have, if only fundamental items exist in the kind of metaphysics sense of these things. And I think the effective realist can just say that the claims of the standard model could well be like that. So to whatever extent, and I guess I'll add that to whatever extent the project of reading ontology off of physical theories has been successful to date, I think it's been successful in this perhaps attenuated but effective sense. I don't think that collapses us into merely saving the phenomena. We're identifying what the stable patterns in the phenomena in the world really are, and we're building descriptions that allow us to make very careful and precise predictions about what kinds of behaviors we're going to find under widely varied circumstances. And to me, that seems to be a good locus for an effective attenuated realism about scientific theories, whether they're quantum field theories, which need to be understood in that way in order to be well defined, or other theories that aren't even quantum field theories. Okay, so.
Oh, there's a few questions. All right. I will start with Adam.
Thanks,
Can you just leave your hands up for a second and I'll just get
This, so it's interesting, and I'm mostly in agreement with you, I think, but one of the questions I have when we kind of, why not divorce the motivations even further? So you say, we can have this sort of effective realism that doesn't necessarily have anything to do with renormalization, and I think that's right. But why tie it, to length scales or energy scales, right? So this, I think this kind of falls into a sort of generalization of Laura's critique that what if we, new theories that have domains of applicability and the scales that are relative there are something that aren't length or energy. And I just think for this sort of approach to be more widely applicable, we can just think of theories with restricted domains of applicability. They need not be put in explicitly into the theory. We can just kind of have external reasons for thinking that they're effective. And so in this case, I just wonder, other than maybe sociologically, it's been inspired by quantum field theory, what sort of connection is there?
Yeah, so I think I can see contexts where something that doesn't explicitly attach the kind of restriction on domain to, say, distance or energy scales in particular could be helpful. At least in the context of the bottom, such as we've got access to it. It's not obvious to me what the alternative could be that doesn't make prejudgments about what precisely this question of what lies below. And so the scales way of doing things seems helpful in the sense that it gives you a pretty generic kind of criterion or a container, rather, in which to search for patterns of dependence or independence across scales. And yeah, so yeah, I'm sympathetic to the possibility of expanding the notion. It's just not obvious to me what the right thing would be at the bottom.
Can I follow up? Yeah, I just, my worry comes from, I mean, there's a couple of worries, but one thing is, quantum, in a theory of quantum gravity.
Just a little bit.
In a theory of quantum gravity, presumably, at least the notion of distance might break down, right?
Yeah.
And so if you want to say, oh, we should be effective realists about a theory of quantum gravity, I don't necessarily think you need to propose a concrete alternative, because it might be different in different theories if the domains of applicability are delimited by different criteria. And I think you could still use a sort of view like this while being even more agnostic about what counts as the relative domains.
Yeah, I think I'm sympathetic to the attempting to identify alternative ways of chunking up domains. I just think that scales have proved to be, like inductively at least, scales have proved to be really critical tools for identifying these sorts of patterns of dependence and independence across different layers of stable phenomena. And okay, yeah, the world could well be such that that's going to give out as the relevant way for making those discriminations, but it's not obvious to me what the alternative tool is going to be that would work well in this context.
Kate is next.
Thanks for the talk, it was super interesting. So I may have just missed a thread here, and let me know if that's the case, but so I'm wondering how the presence of Landau poles fits in with your story. So you disentangled the perturbative ultraviolet divergences from motivation for taking an effective field theory interpretation. My understanding is that Landau poles can be, the existence of Landau poles can be like a non-perturbative thing.
Exactly.
So do you think that this disentangling bears on the motivation for taking an EFT interpretation, coming from existence of land apples?
Yeah, so part of what I was trying to say is that while these sorts of perturbative divergences strike me as mathematical artifacts of perturbation theory, and mathematical artifacts of perturbation theory don't seem like the kind of thing that could motivate you one way or another to revise what you think is going on physically. Things like land apples strike me as a physical component, or part of the physical content of the renormalized theory. What you find when you find a land apple is that once I've executed my perturbative renormalizations and I consider how the theory scales, what I find is that there's no way to renormalize the theory and let those couplings scale in such a way that I get a theory where the couplings remain finite for all values of the energy. At some finite value of the energy, the physical couplings diverge. And that strikes me as unphysical. That's not some mathematical bad behavior. That's the theory telling you that it's not consistent across all distance scales or energy scales. Thanks.
Alex.
Yes, thank you. So I wanted to ask about the strong statement they make that the perturbative UV divergences have nothing to do with say the UV behavior. I mean, it seems clear that, as we can see in QCD, right, that they're not a sufficient condition for UV non-finiteness, but they do appear to be a necessary condition, no? And that also seems to be like, for example, in string theory, where one doesn't have perturbative UV divergence, the assumption is that because they're a necessary condition, that also implies UV finiteness on some sort of non-perturbative level. So there does seem to be some sort of connection there, or would you argue against that they're a necessary condition for UV non-finiteness?
Yeah, so as I said, I think it's probably obviously too strong what I'm saying here. I chose to say it obviously too strong for precisely the reason that what I'm after presently is a way to be more precise about what that connection is. I'm not certain that even as that they function even as a necessary condition. Obviously, there's cases that seem to suggest that, but I don't feel yet like I'm in a position.
We have no examples of theories without
right. But that's a case by case kind of argument, and what I want is a demonstration that the presence of that sort of feature entails, in some sense, the other behavior, rather than kind of like look at all these cases that we've got where that seems to be the behavior.
Wayne.
Thank you for this. So, the last part. So the essence of effective realism is that we should take even our best theories to have limited domain and be a non-committal over what they say in regions when we have beyond where we have empirical access. I can totally get on board with that. You also said this is something that we came to recently. So my question is, what part of that is new? If you look at the history of science, it is a history of people explicitly thinking that their theories have limited domain and being agnostic about things beyond rapid empirical access. So the ancient astronomers adopted the compromise of Geminus, where they said, okay, we're going to do models, but we don't have access to what's up there in the heavens, so we're not going to be committed to the planets are actually doing this. Newton was explicitly non-committal about whether matter is continuous or there's smaller parts. He says in the fourth rule of reasoning how we're supposed to take the theory of gravity, that it's at least approximately true in the domain in which he's applying it. He's explicitly open it to having limited domain. I go on and on and on.
Yeah.
But so what's new about this?
Yeah, so fair. I think you're probably right that there's all kinds of ways in which people have advocated for explicit restrictions on domains of applicability. I think there are instances where people have not done that. I think the aspirations of quantum field theory are, the initial aspirations of quantum field theory count as directly transgressing against that kind of methodological dictum. But okay, so that's just to say, some people do it, some people don't. That's not very helpful. I guess maybe the more helpful thing I can say is that maybe what's new here is a collection of methodologies that allow one to be very explicit about the way that one is making this, the way one is making this requirement about the domain of applicability inside the mathematical machinery of the theory. And what it gives us is tools. What that gives us is tools to be really precise about what sort of patterns of dependence and independence across scales one should expect to find. And so, yeah, I don't mean to claim by any means that the idea that a theory might not apply across all scales is fundamentally new here. I think what's maybe new are the technical tools to be sharp about that inside the technology of the theory.
And while we've got this thing, I don't understand this sentence. What we get wrong what objects are if only fundamental items exist. What does that even mean to say only
So
fundamental
imagine you're
items
talking
exist?
to this. I have these conversations a couple times a month with various metaphysicians who tell me that when I say that this lectern is solid, I'm saying something that's not true in the sense that what's here is not a lectern. I've got atoms arranged lectern-wise, and the point, all I'm saying here is that the standard model microphysics that we now imagine as, in some sense, the bottom layer of reality, seems to me like the kind of thing where we have no reason to think it's not going to suffer the same fate, where
Okay, so I guess my
Okay,
question.
I have
okay.
a long list of people
Alright.
who want to ask questions
Okay.
here, so, Emily is next.
Thank you. Yeah, so I mean, I think I agree that, in a sense, realism has always been somewhat effective in this way. But, when you put it a little bit like this, it sort of leads to, for me at least, worries about the sort of epistemic security. So, I mean, if you're committing to this sort of middle level with literally no idea whatsoever what's underneath, it seems like you're putting a lot of faith in your expectation that what is underneath is not going to interfere too much with the middle level and isn't going to break the stuff that you think you know. If you insist that it all supervenes on some ultimately unknown foundation, there are surely some ways the foundation could be that would just undermine all of our scientific knowledge, considering cases where the bottom level interferes with memory and records and stable macroscopic reality and so on. So is that something we should worry about or just maybe ignore? I'm not quite sure.
Yeah, so I take it that that's what's animating Richie in this worry she's expressing, which is that what I get from the renormalization group is a principled demonstration that if I put quantum field degrees of freedom down below, then that's not going to spoil the relatively long distance physics, and all you get from the effective field theory treatment is a principled demonstration of that sort of independence. But what's being claimed by the effective realist, you're right to point out, is something stronger, which is that whatever you put in down there, it's not going to spoil the relatively long distance physics. And there's a sense in which you're right. That's sticking your neck out and saying that I'm going to make realist commitment, which I can't rule out eventually being spoiled by what's going on in the shorter distance physics. But to me, that's part of what distinguishes the view from a kind of empiricism that just says, like, look, what we get from the standard model is a nice algorithm for predicting the outcomes of these scattering experiments, but nothing further about whether the kind of ontology that we use to describe what's going on in those scattering experiments actually tracks what's there in the system. So I think I guess I'll just say I think you're right. This is at least a substantial portion of what distinguishes effective realism, as I understand it, from just a kind of empiricism. And it is a place where we're sticking our neck out, and it's the kind of thing where we could turn out to be wrong. But that's if you're advocating for realist positions, that's what you're opening yourself up to, is the possibility that you haven't got the ontology right, and that eventually your picture is going to be spoiled by future developments.
Okay, next up, Carlo.
Let me put it this way. I have a lot of sympathy with the sort of effective realism. The two objections that come to my mind. One is that I've been a physicist for 40 years, and I never heard any of my colleagues thinking that the standard model is bottom layers of reality. And it seemed to me you have a straw man out there. I mean, we went very, very rapidly from strong interaction cannot be understood with quantum field theory to standard model is obviously incomplete, there's much more that we're missing, to quantum field theory is probably not the right way of thinking about the world for one or the other reason. So, and this specifically, let me go to the bottom line. This is along the line of Laura or Adam also. It seems to there's a confusion between below and behind. So that the idea that behind what we know, there's most likely something else that we don't know. It has been without the science, as Wayne was saying, since ever, and I think it's very healthy. And if it's true that somebody has tried to say, well, maybe we're at the bottom of the, but that's a minority position, I think. The idea that what is behind that we don't know must necessarily be below, I think if you're pushing to that, is not right. Because you mentioned quantum gravity and you mentioned the asymptotic safety problem, which it's an hypothesis, one of the current problems of quantum gravity, and it would go in the direction you say, continuing the idea that there is something below that we don't understand. But the other two main ideas, and by far dominant approach to quantum gravity, string theory that was mentioned, goes exactly in the other direction. If string theory is right, there is a sense in which we know that in that direction we've got to the end. It doesn't mean that there aren't things we don't know. Well, if you take a look at quantum gravity, if it is right, and string theory could have been strongly supported, say if we had found supersymmetric particle where it was expected, right? And then if so, we would take it as a reasonable, partially empirically supported hypothesis about nature. Suppose loop quantum gravity was confirmed by some measurement about early universes. So we take it as a reasonable hypothesis about nature. Then it's saying that the specific hypothesis of quantum field theory, which is that there is an infinite tower of degrees of freedom forever in the small, is just not right, not realized in nature. It can still be that there are other interactions we haven't access to. It can still be that we figure out the quantum property of gravitational field, and still at some intermediate energies there are interactions we haven't met to, so there is still behind it. But why shouldn't it be below? You had a slice where you said that even if we had a quantum theory of gravity, we should always think that there is a smaller degrees of freedom. I think this doesn't follow, apart from everything could be true. So the core of my point is that it seems to me that you're overemphasizing specifically the issue of scale, which is attached to a specific event in this game about an organizational group and so on and so forth.
Yeah, okay, so there's lots there, and I don't know that I'm gonna remember all of it or get each piece, but
Pick one thing, because I want other people to.
okay. So I guess, yeah, this is similar to what Adam said.
Yes.
And yeah, as I said, I'm sympathetic to that. It's not always obvious to me how to write down an alternative criterion which is generic in the relevant sense. So if you come up with some particular quantum gravity scenario, that can show you what the alternative situation could look like in such a way that it would show up in what we can see. But if one is trying to express the sort of thing that I take it that the effective realist wants, which is that we've isolated some kind of stable realm of the phenomena, the tool that we presently have for articulating that is this notion of scale. And that's not to say that, as I was telling Adam, that's not to say that that's like the be-all end-all and that we should continue to expect that to be the relevant one. It's just, given our current situation, that's what we've got. Just one other, I know I'm supposed to say just one other clarification. I was only considering the asymptotic safety scenario in quantum gravity when I said that thing about continuing to expect it below. I'm completely on board with the idea that alternative quantum gravity scenarios could make this situation look rather good.
David.
Can we fight back a little bit for
Yeah.
the orthodox catechism, not for all of it, by any means. So the place I'm uncomfortable is the idea that there's. Oh, thank you. Place I'm uncomfortable is the idea that it's only of mathematical artificial significance that we find the divergences here. So suppose I'm doing quantum field theory. I try to write down my theory, even non-perturbatively. I try to write it down as half integral, whatever. I find that going to infinity is causing me mathematical trouble. But I'm a practical man, I don't care. The theory obviously isn't trustworthy to infinity anyway. Suppose it's trustworthy down to lambda, write the theory down at lambda. Okay, it's perfectly finite, no distributions, no infinities, no singularities, well defined. But there's a different problem, which is that if it's a renormalizable theory, say it's QED, every e-fold of momentum modes contributes the same order to the dynamics as the previous e-fold. So there are big contributions to the Hamiltonian, to the dynamical properties of the particles, etc., coming from the high energy physics. And I don't know anything about the high energy physics. I cut it off in a completely arbitrary way. So prima facie, I've got a big problem, which is that the high energy physics is having, which I don't know, is having a big influence on the low energy physics, which I do know. And then it's a huge relief to realize that I can incorporate all of that high energy dependence into the relation between a finite number of bare parameters in the underlying full dynamics of the theory and quantities I can measure. And so I now understand physically how I've got a well-behaved low-energy theory, even though A, I'm ignorant of the high-energy physics, and B, the high-energy physics has a big dynamical effect. And that seems, and then we see, and in situations where we actually know the high-energy theory, whether in kind of effective field theory, QCD, or in solid-state physics, we can see that playing out perfectly explicitly, and we can see how the measured parameters differ from the parameters in the high-level theory. And all that seems important physical insight, and not just a matter of having got the math wrong.
Yeah, so I think that this is kind of coming out in our discussion yesterday. It strikes me that that's another way to get to what strikes me as actually a similar conclusion, because in the way that you've regularized the theory there, at least as I understand it, you've removed this kind of piece of the story that was the thing that if you set up perturbation theory alternatively, it gets in the middle of the story. On your story, it's just you've cut it out and you get to the what is physically salient by other means, and I'm perfectly happy with that. All I meant to suggest is that sometimes the way that people talk about this alternative way of developing perturbation theory that does engender this collection of assumptions strikes me as somewhat misleading.
So I think that's just briefly. I think that's fine. The only thing I'm worried is missing in the story
Yeah.
is the fact that renormalization, like, you know, the adjustments of the constants to absorb high energy physics, is a real physical thing that's going on. We don't want to hide that. We want to understand. We want to recognize and understand that that's happening.
Yeah, and I think that that's included in this alternative story. It's just included in a slightly different way. And so, yeah, I guess I didn't emphasize this as I was saying this out, but so there's this mathematical, what strikes me as, at least as a mathematical artifact, the singular products of distributions, what's physically salient about the renormalization procedure, however one ultimately decides to regularize and then effect a renormalization, is precisely the kind of scaling behavior that the theory exhibits. And however you get the theory to divulge that information to you, I think that's what's physically important about renormalization. That's what ultimately bears on the question of whether there could possibly be a continuum limit of the theory. And those are the kinds of physical reasons which get mixed in with these questions about what are the good kinds of motivations for effective field theories.
Mark.
Would you say that effective realism is also the best attitude to have with respect to, for example, cosmological theories that make claims about the extremely far future, even that you can't have access to that future?
Good question. I don't know that I have a well worked out view there, just partly because of my own ignorance about current cosmological models. That would be an example of the kind of thing where if that's what the domain of applicability is, if that's where the domain of applicability gives out, it looks quite different, as Adam was pointing out, than the kinds of restrictions on the domain of applicability that EFT technology gives one the resources to be precise about. That's not to say that it wouldn't be an interesting place where one could identify one could identify an interesting version of the same thing going on, but none of that's particularly helpful. I guess it seems to me like the kinds of reasons that people typically adopt for thinking that far future physics is going to look similar to present physics are different kinds of reasons than the kinds of reasons that people use to reason about the kinds of physics that we find on this scale and how it relates to the kinds of physics on this distant scale. And they're different in that we've got a lot of experience of differentiating the physics on distinct distance scales. We don't, to my knowledge, I'm sure someone will correct me if I've got this horribly wrong, we don't have information about physics changing on temporal scales in that way, which is not to say that that couldn't happen, or that's not an interesting scenario, but our kind of our access to those scenarios strikes me as quite distinct.
Chris.
So thanks so much for the talk. There's a lot of interesting stuff. I wanted to just come back to one of the questions about the thinking of UV divergences as mainly a mathematical artifact. And so I think this is related to James's talk in the sense that you're kind of not taking the story as an entirely fanciful story. As part of the argument that there's an account in causal perturbation theory that allows you to say, here's the mathematical location that's sort of, the product of distributions. But I was wondering, I mean, this is just reflecting on when you learn QFT, there's usually like a huge slew of techniques, and some of those seem more straightforwardly mathematical rather than physical, so like dimensional regularization. I'm wondering if you can supplement the story by looking at those kinds of cases, or how you think that plays into it. It's really just, it seems like you could make a similar kind of case, again, naively thinking about some of these other renormalization techniques, that it again looks like it's handling a sort of mathematical divergence that doesn't have the connection to physical properties of the theory that you were trying to isolate.
Yeah, so I think that's an important project which should eventually somebody ought to do, is work systematically through, forget about renormalization, just focus on all the different ways that we use to regularize theories, and the different kinds of physical features of the situation that those distinct techniques allow us to make salient. And yeah, there's lots of things. There's things we can do with dimensional regularization that we can't do when we regularize with a lattice or a cutoff or whatever it is. And yeah, I'm afraid I don't have anything particularly instructive to say about those things, besides that, yeah, my guess, if I'm right about the claim that the perturbative divergences, at least, or at least most of them, are artifacts in this sense, then it shouldn't really matter how you regulate them. What you're ultimately after is what this physically salient stuff that renormalization is getting at, and how you get the theory to give you that is should be invariant with respect to what how you choose to regulate.
Yeah, and I mean, the crude thought I had was just that you mentioned that because introducing a cutoff can make it seem more physical, that you know, that could be a source of confusion, that in some of these other regularization techniques it might just be more transparent. But I don't have a specific proposal to fill in there. It was just more.
Yeah, no, that's fair. I think you're right. Yeah, so something like nobody's tempted to interpret dimensional regularization as like this physical transformation on the theory, because it's clearly something where we're just mathematically manipulating integrals in order to isolate infinite contributions that are problematic, and then manipulate expressions in a well-defined way and get at the physical stuff that we need to in. But yeah, beyond that, I don't know that I have much helpful to say.
Okay, so it's time for coffee. Anybody who's still on my list should write down their question and save it for the panel discussion. It's coming later. So let's thank Mike again.